Okay, well, thank you very much. Next, we have Antonia Drescher, that's how I pronounce that, sorry, from the Max Planck Institute on imaging faint stars in the Galactic Center with gravity.
Okay, I hope you hear me well. And I'll share my screen now.
Yes, we hear you. Thank you.
Okay, perfect. Okay, do you see my slides?
Yep.
Okay, perfect. Okay, so first of all, thank you very much for giving me the opportunity to present my talk with the title Imaging of Faint Stars in the Galactic Center with Gravity. I'm Antonia Drescher. I'm a PhD student at the Max Planck Institute for Extraterrestrial Physics in Garching in Germany. And I'm giving this talk on behalf of the Full Gravity team. So the center of our Milky Way hosts the supermassive black hole Sagittarius A star. Tracing stars and orbital motion around this black hole gives the unique opportunity to test general relativity in the vicinity of a massive black hole. In the previous talk, Felix Wittmann presented the results from gravity observations on the Galactic Center from the last years. And these results include the detection of the gravitational redshift and of the Schwarzschild precession in the orbit of the star S2, as well as orbital motion close to the last stable orbit during a flare. And in my talk today, I would like to focus on results that we obtained from observations on the Galactic Center with gravity last year. In 2021, we monitored Sagittarius A star and the stars around it over a period of 4 months. So in March, May, June, and July. And we detect the stars S55 and S29. And we confirm the trajectory of the star S62 with a magnitude of 18.9, which is slowly approaching the black hole. And the to-date deepest images of the Galactic Center revealed a previously unknown faint star with a magnitude of 19.5. And we call the star S300. And it moves at high angular velocity to the west. So you can see it here in March, in May, and in June. And then in July, it is already too far out from our pointing. And we were impressed by how many stars we see and that we can detect an even fainter star, that in July, we moved our fiber to several pointings, 10 milliarc seconds away from Sagittarius A star. And each circle here represents our pointing. So in the central pointing, we see Sagittarius A star, S29, S55, and S62. And then we followed S300, which we can see here in the so-called midpointing. We observed S38, where we see S63 and S60. We also did a pointing to the northwest of Sagittarius A star, where we see S42, and we pointed to S2. So we observed, or we obtained the first mosaic of the inner 100 milliarc seconds around Sagittarius A star. And for imaging, we use 2 different methods. The first one is the method commonly used in radio interferometry and adapted to gravity galactic center data. And here we use the CLEAN algorithm, which is implemented in the software package ACE. And the dirty map that we obtain from CLEAN is purely based on the visibility amplitude and the visibility phase. The source identification is done by the brightest pixel in the residual image, so no prior knowledge is needed. So CLEAN here is a human-guided source identification. The other method that we use is a newly developed imaging tool, which is called GR. And GR is based on Bayes' theorem. And here the idea is to minimize the posterior probability distribution, which is proportional to a likelihood times a prior. So here we need a prior. And GR uses either the visibility amplitude and closure phases or the visibility amplitude and visibility phase for imaging. Additionally, GR accounts for instrumental effects, such as field-dependent optical aberrations that are introduced in gravity. Both imaging tools are still under development. So for CLEAN, we are working on implementing a correction of these field-dependent aberrations. And for GR, we are working on mosaicing. So we want to put together different pointings around Sagittarius A star and then image them in one run. And here we show an image of the so-called midpointing with both methods. And in both, so this is where we followed S300, the new star. And we see S300 in both imaging methods. We also see S63 and S38, Sagittarius A star and S29 here. Also GR shows S55. However, for clean, it is already too far out from the field. Due to gravity's high angular resolution and high precision, we can measure positions of stars at a level to a few microarcseconds. And with the data from 2021, we are able to improve the significance of our detection of the Schwarzschild precession in the orbit of S2 to 7 sigma. So here you can see the new data points from 2021. And also in this year, so this is seen in the plot to the right, we observed S2 in March this year. And S2 is is detected where it is expected from the Schwarzschild precession. We fit the data of the 4 stars, S2 here in red, S29 in dark blue, S38 in black, and S55 in light blue. And we find that they perfectly agree with general relativity orbits around a single central point mass with 4.3 million solar masses. And our 4-star fit, together with the precession of the star S2, we can get a limit on any extended mass component in the galactic center. And we find that any extended mass inside S2 or inside the S2 upper center must be less than 3,000 solar masses, which is 0.1% of the black hole mass. In 2022, we observed the Galactic Center twice, in March and in April. And our goal for the observing runs in this year is to expand the observed field around Sagittarius A star. And this is to follow the orbits of known stars, but also to potentially detect previously unknown faint stars. And the image here to the left is a mosaic from March this year. So we pointed to Sagittarius A star, where we see the black hole in S62. We pointed to the stars S38 and S2, and also to the west, where we see S55 and S63, to the south with S24 and S60, and to the north with S29 and S42. And for the upcoming observing runs, we already prepared further pointings. And now we want to extend our field to the east. So the goal is to obtain a mosaic of the inner 200 milliarcseconds around Sagittarius A star. And the next major goal for the Galactic Center is to measure higher order relativistic effects due to the spin of the supermassive black hole. And this could be achieved by measuring the effect of the spin on stellar orbits. The spin effect, but since the spin effect falls off with r to the -3 from the mass center, it is currently not clear whether the known stellar orbits allow for a detection of the spin of the black hole. However, a fainter star at smaller radius to the black hole could provide an opportunity to actually detect the spin. And Weisberg et al. 2018 determined that we would need an S2-like star, but with a 10 times smaller semi-major axis. And so here, the orbit of S2 is shown in red, and the orbit of this hypothetical S2-like star in blue. And the signature that we would measure is the detection of the rotation of the star's orbital plane, so here. And this is different from the Schwarzschild precession, where we see a rotation of the orbital ellipse in its plane. So thus, finding faint stars close to the supermassive black hole with imaging is crucial for achieving this goal. And the effects of the spin would reach a level which is accessible with gravity plus astrometry. And together with ELT spectroscopy, we could complete orbit monitoring, and this will bring us towards the spin of the supermassive black hole in the center of the Milky Way. And with this, I would like to thank you for your attention, and I'm happy to answer any questions.
Thank you very much. Do we have any questions? Conrad? do you have a question or is your hand still up from last time? Oh, okay. Anybody have any questions then for the speaker? Please go ahead. Please give your name and institute.
Hi, this is Gail Schaefer from the chair array. I just had I was just curious why the beam shape changed between the clean image and the GR image that you showed.
Yeah. Okay, yeah, thank you for your question. So in GR, the beam change or the beam shape changes because in GR, the idea is to really estimate the probability of finding a star on each pixel. So here we infer flux on a pixel position where the probability is higher. So this is like more a representation of where flux is inferred at the pixel position.
Thank you.
I hope that is, yeah.
Oh, Conrad would.
Yes, okay, Conrad Tristram, ISO Chile. I did actually have a question, but I was just clapping my hands at that moment still. So thank you for the nice talk. For the 2022 measurements, did I understand you correctly? You didn't make it explicit that you did not detect S300? So
we did detect S300. However, the west pointings that we have here, we don't have so many exposures. So we need to integrate longer. And currently we're still working on it, but we see it, we definitely see it, and also in both codes, but the exact position is still to be determined, to be estimated.
Okay, thank you.
Okay, any last questions? No? Okay, well, thank you again for the nice talk.